This is so much nicer than particles. The technology. It's even good. Good. See you guys. Sure, now on. All right. So warm up. I wrote this down so that we. Good. So. What I want to, what I really like, guys, have a good sense as to how campus spaces work. As I said last time, it's very useful. This knowledge is really useful. Modeling, we have a constraint. How much parameters, but there's some relation between some parameters. I gave an example in notes where it's like take energy, mass, and velocity. Formula, say kinetic energy. Formula relating these three things. 1/2 mv squared. But let's say your function is a function of all three variables. Well, you really only care about it on this constraint where this equation is satisfied, because other values of those parameters aren't going to be valid. So it's helpful to understand tangent subspaces at points in order to do certain optimization on these constraints. So as a warm-up, what I want to do, let's just go back to what we started with last semester. It's a matrix equation, very simple matrix equation. This is an implicit function, right? Or this is an implicit equation. Or you can think of the set of points satisfying this equation as being some constrained space, right? So you've got X here, which is given by, so let me rewrite this equation. Particular this equation. Equation, I mean, you can think of it as it's a linear system of equations. So you have two equations, right? And 4 unknowns. And you're solving it. And if you, what is that going to give you? Like, generally speaking, it depends on the ring, but in this case, what kind of space are you going to get? The solutions of this equation. Answer that question. Close. So we have, so we're, how many parameters do we have here? X1, X2, X3, X4, right? We have four, we're in a four-dimensional space, and we have two equations. First equation is given by 1 times X1 plus the square root of 3 times X2 equals 0. That's it. We have one equation there, and we have another equation, square root of 2 times X3 minus square root of 2 times X4 equals 0. So two equations. Each time you write down an equation, if it's sort of sufficiently general, what it's going to do is it's going to cut down the dimension by 1. So if you're in 4 dimensions, your first equation cut down the dimension by 1 and give you a 3-dimensional space. Then you have another equation that will cut down that 3-dimensional space by 1 and give you 2 dimensions. This is generally, I mean, if you give the same equation twice, right, you're not going to do. So that's essentially a rank computation. But here you'll get a 2-dimensional space, linear space, inside of 4 dimensions. It's a plane. It's a plane. Yes. Well, the way you're thinking is, no, it's actually close, right? Because I think you're thinking, well, maybe you're thinking sort of a rank nullity type thing. I mean, where you do have to, in general, if you just have a matrix equation like this, you have to kind of, if you want to know the dimension, the dimension is essentially, the nullity of this matrix. Right. And so by definition, and so if you know the rank, which is kind of easy to compute, you can see the rank is 2 here, because this is clearly linearly dependent of this. You can see that the nullity equals 2. Maybe the count on the rows in the columns. Just apply that up here. So we get a plane in R4. Now we know it's a plane, but we don't necessarily know what that plane is. Like, can you give me a single point on that plane? All right, well, what we did in the first part of last semester was we went through this row echelon form business. And in fact, we parameterized that plane. So that was this, I just did the exercise. We have 2 free columns here. So if I put 2 free variables, T1, T2. And when I put T1 and T2 into this matrix equation, I get this. I get that this quantity equals this, and this quantity equals this. And that allows me to solve these bound variables or basic variables in terms of free variables. So I write them down here, and this gives me my solution. Then when I return back to this expression, I can write down the solution here. And now I have a full parametrization of my set of solutions, right? So given any 2 parameters, T1 and T2, I get a solution to this equation. Those 2 parameters do indeed parameterize. They give me a grid on my plane, on the solution space that is my plane. They coordinatize that plane. Okay. All, ancient history, memories of good times. Linear algebra. Because I have. Okay, so okay. So now here I'm making these steps. So if we think of this space, so we actually think, so we have an equation, it's a constraint, but we can actually think of the space itself of the solution set equation. In other words, the kernel, the nullity of A, or the kernel of multiplication by A, however you want to put it, it's some space inside of R4. And as I said, as we found a moment ago, it's a plane in R4 and it's given by this constraint. And the whole process that I just reviewed was giving a linear parameterization of this substance. We actually go from the implicit equation to a linear equation. You can write down this. Okay, so here's the parametrization. Right, x of t is a function. Parameterization is a function of parameters. It takes the inputs of the parameters and outputs some kind of value. Solves the equation,
And if you look at this, you can see that this is actually the same as multiplying by this matrix. So this parametrization is in fact just multiplication by this. Everyone agree? Everyone's happy? Or at least satisfied with this? Happiness is so hard to ask. Okay. Okay, that was linear work, which is not that interesting, but is very satisfying that you can do it. Okay, now let's go to the denominator. This is related to a question on the home. So I want to look at a donut. Right? We're going to look at a donut. It's a donut in 4-dimensional space. Okay, 4-dimensional donuts. We're in 4 dimensions. Let's put our donut. Not quite the same thing. Now, if you think about a donut, and I have thought a lot of donuts in my life, as many mathematicians have. What happens? What is it? What's one way of thinking about a donut? Well, you can think I've got a circle. When I say the donut, I mean the surface of it. I've got a circle. I've got, in fact, a circle of circles. You take that circle and wrap that circle. Get it done. Now, I want to actually give this with equation. Now, there are, a lot of infinite ways of doing this, but I'm going to give a very simple way. And I'm just going to say, okay, from that circle across circle picture, I know how to write down the equation for a circle in the plane. You guys all know how to do that, right? X squared plus y squared equals 1, a unit circle. So let me just kind of divide up 4-dimensional space into two 2-dimensional spaces, write an equation for the circle in one of them, and write an equation for the circle in the other. I have 2 constraints, and the solutions to these 2 constraints gives me, in fact, this a donut, a very symmetric donut. It's also called a torus. It's also called an elliptic curve. That's the elliptic curve. Well, I think that's the case. These are good examples. If you're interested in spaces, in like higher dimensional spaces and stuff, Cori are very interesting. Especially. That's not at all interested in spaces. No, forget that. All right. We're gonna have to be. Okay, so now I want to consider a particular point on this curve. On this torus. I want to consider a single point on this space, and I want to find its tangent space. The donut, the torus, is nonlinear, right? It's not a linear space, and you can, so there's it's not a vector space. But if we take a point on it and we consider the tangent space of that point, that in R4, that's a copy of R4. And then we can consider the tangent space of the torus, which is a plane. Everyone with me? The question is, how do we find that tangent space? Well, let's take a look. We want to find this. There's 2 kinds of tangent spaces. One is really kind of a legitimate one, and the other one is sort of something you teach. There's the tangent space, which we think of as a linear subspace of the tangent space of the point. And then there's the affine tangent space inside of R4 itself. People understand the difference between these? Let me give you an example that we can see. Let's say we have a curve. We have some point. Now there's this curve is in R2, right? So here we have R2. Now R2 has an origin. And now, when we think of that point that I just drew, there's like, well, there's a little tangent space R2 at that point, which is, again, this is the these are all vectors that, start at this point. It's a little copy of R2, where now we've centered the origin at that point P. It's its own vector space. It's not R2 that we started in. R2 that we started is called the ambient space. But we have this actual tangent space. Now I can consider the tangent line to this curve as the set of tangent vectors that are in this tangent space. That's the real tangent space, what I'm thinking about. And that's a subspace of TP of R2 by writing that. Or I can actually translate that line and put it into my ambient coordinates here. It just is a translation. You're just moving, so you'll get a slightly different equation. It'll look almost exactly the same. Half lines. Notice that this, as a subspace of the tangent space of R2, that line is linear, a linear subspace. Whereas it's not linear if you think of it as a subspace of the ambient space, because it doesn't mess with this word. Translate. Here. So if we want to find equations, we need to kind of distinguish between those two, make sure we know which one we're talking about. It's not a big deal, but it's all right. So I want to find the tangent space of this affine of this torus. I want to find this tangent space of this torus. So there's two ways to go about this. There's two ways. There's the easy way in general is to do solution one. So consider the constraint. These two equations can be written as a single constraint. Namely, I just want to take a function of 4 variables to the plane. And I'm going to say, well, my space X here is just all of the points that are sent to this point, 1, 1, right? That's how I sort of define this. X is in fact the inverse image of this single point in the plane as a map R4 to R2. Well, it's just the definition of what it means. What does this mean? This means that's also called the level set. It's the set of all points U, V, X, Y. So that when I take f of U, V, X, Y, I equal 1, 1. That's the definition. And that's true because this is kind of how these equations. Okay, so now I have a function. This function is differentiable. I can take its Jacobian matrix. Yes. How do I define it? How would you parameterize it, or how would you define it?
Like you have X as the equation.
It's an R4.
It's an R4. What would that look like if force existed?
It does exist, but it's just it's a kind of more complicated. I mean, it's not that bad. In polar coordinates, it's not hard. It's hard. Sorry, cylindrical. It's not so bad.
So we're using R4 to express.
I wanted to give you something interesting.
Some stuff to chew.
Huh?
Some stuff to chew on.
Some stuff to chew on, yeah, exactly. All right. So what do we do? I mean, this is a simpler example. That's kind of. So we have this function, and what the point is we can take its derivative, find its Jacobian matrix, which I've written out here, and then I can evaluate that at the point, right? That we're interested in. This is the point that we're trying to find the tangent space at X at. And that equation will depend on which point. So I put this point in. I get this. And now. Here's a question you ask. Is this matrix? Jacobian matrix of full rank? Full rank means it has the maximal rank it can have. I think it has the maximum. That's the maximum. What's the rank of this? 2. Yes, right. It can't have more than 2. Only has 2 rows. So the answer is yes. And then there is this black box. You guys know about black boxes? Okay, this is an expression mathematicians and scientists. They call them black box. We call them black box, which is theorems that we don't really have a great sense of the proof. Now I have a good sense of proof for the function theorem. This is something you'll learn in an analysis. Okay, so I'm not going to prove that, although some courses we're not going to prove that. But there is this theorem called implicit function, which says that if you have something like a situation like this, where you take the Jacobian matrix, full rank, going from a higher dimensional space to a lower dimensional space, then in fact, there is a chart. There's a nonlinear chart of the levels. So it's saying that essentially there is a 2-dimensional surface near the point P that has a chart that satisfies this equation. That's the theorem. Now, when you have that theorem, and let's assume that theorem. So we put it in a black box. It says later on you'll learn the proof of that theorem. You'll understand that theorem better. But we're going to accept that theorem. When you have that theorem, what it will imply for you is that the tangent space to your level set is in fact the kernel of the Jacobian matrix. Kernel. In other words, it's the null space of the Jacobian matrix. Why is that true? Well, that's true because of the chain. That's true because of the chain. Because if you take any curve, right, in your level set, and you compose it with that, like we did last time, you get a constant function. Which means if I take the derivative of that composition, I should get 0. Which means that the derivative of that tangent curve is getting sent to 0 when you put it into the Jacobian. All of those tangents to the curves of your level set, they're getting sent to 0 under the Jacobian. So that whole tangent space is like that. Okay, if you believe that, and you should, because it's true, we have the solution. We have our solution. What the tangent space is as a subspace of our TPR. Right? Why? Because, well, I started off with a warm-up, which was this matrix. Found the kernel. In fact, explicitly parameterized it by this equation. It's parametrization. That will give us. Now, you can say, all right, well, what do I mean by this? Well, here, in fact, what is this? This is going to be, so if you write this out, this first, yeah, here's what I want to say here. This first column, so if I write it out, I can write it out as T1. Remember, these are tangent vectors. Oh, sorry. So, what am I trying to say? I just want to say, we have chosen certain coordinates here. And the point is I want to explain what these coordinates are. So that first column is really minus the square root of 3 times del u plus del v. That's the first column. And the second column will be del x, del y. Remember, these tangent vectors are like directional vectors, essentially. So you can think of these are the actual, I mean, we're using coordinates using this basis. Del u, del v, del x. That's our base. So that's what this means when we write it down. Just making value. Okay. Not too big of a deal, I just. All right. So we get this parametrization. That's one way of solving this. The other way of solving it is parametrizing X itself. You can parametrize the actual torus, right? As we said, this torus is a circle times another circle. So we can give ourselves two parameters, one for the angle of the first circle, the other for the angle of the second circle. And then we can essentially, take this piece of paper and do what you do in math circles. As we know about math circles, I don't have any paper too mature for paper. Because I can't even do it with paper, so it's kind of silly. But yeah, you take paper, here's your coordinates, and you one like this, you could make a cylinder, and the other one, because takes your actual plane of coordinates and maps it to the 4 dimensions. It's a nice map. We just use the parametrizations of the unit circle in both cases, and I have my two angles, theta 1, theta 2. We note that if Q is equal to pi over 3 and 3 pi over 4, I put that Q into G, I should get P. Right. The value of this parametrization at Q is P. So this is, and now what I want to say is, well, G, yes, go ahead. Via. Yeah, I can parametrize it with this function. Now, Gi also is a differentiable function. I can take the derivative of G. It's right there. And then I can evaluate that derivative at the point that I'm interested in, Q.
The X and Y free variables.
Way up here. So if this is almost in reduced row echelon form, we just got rid of that, right? And so these pivots are the bound variables, the basic variables, and the frees are everything that's not.
Oh, that's right.
Wait, am I doing the right thing here? What are you asking?
It looks to me like the first arrow that you have is pointing to
sorry. Yeah, I missed that. All right, good. So we can take the derivative of G. I did it here. Then I can put in Q for theta, pi over 3 for theta 1, 3 pi over 4 for theta 2, and I'll get this matrix, although what do you think of that matrix? I didn't finish writing this. Well, you guys think of that? Be familiar about it? Yeah, it's half of the parametrization we have up here. This matrix and this matrix are almost the same. One is just scaled by 2 of the other. In fact, the tangent space at P, or maybe I'll write it at G of Q. X is going to be parametrized. Right, is parametrized. And let's all right. Let's distinguish from the other things. Like I shouldn't say it. What's interesting about this is that there is work, there's some linear algebra work involved in solving that linear system equation. You just have to reduce the row echelon form. It's not much work, but there is some work. But you get it automatically if you have a parametrization. Just take it. Of course, having a parametrization is generally a lot harder. So that's a much harder. But sometimes you're just given one. Start with it. Yes. How did I get, well, so I set this problem up so that, but in general, you would have to look and you would have to say, okay, here's this point P. What are the theta 1, theta 2 coordinates that get sent to? And so that would be, you would take some inverse trigonometric functions of, you know, the X variables. Vice versa. Calculated that. Yes. What's about yes? Okay. How are people feeling? I'm feeling annoyed that I don't have.
I mean, if you want to try putting.
No. Let's not kill. I used to have carry some. Huh? All right, well, you guys can still work without. All right, so what I wanted to do now was give you guys a problem of this, a little problem of this nature. Problem. And I started talking about it last time. And see if you guys can go. Now, one last thing I want to say is, so these, as I said, these are subspaces of a tangent space. If I wanted a subspace of the ambient space, a plane that lives in the actual space R4, not just the tangent space of P, I just have to add P. Right. So in other words, if I want, what I'm saying is in R4, I can parametrize this space. I can consider, say, Y of T1, T2. Tildes here. I'll just say, okay, we'll take the actual point, which is given by whatever coordinates vector point 1/2. Right. Take this point and add essentially this, you know, I mean, derivative, so add this matrix. That's T. This gives a subspace in R4, an affine subspace, because you're translating, so you're not necessarily going to do it. This would give the actual, what I think in a Calc 3 class you would write down as the tangent space. Usually, or even in Calc 1, right? In Calc 1, when you say what's the tangent line to a curve, that's usually in the actual graph space that you're slightly different. But phenomenal. Okay, guys, so here's the problem. Yeah. Break into groups of two, I don't know. All right. So last time, I think I wrote down, did I write down the spherical coordinates? This is partially spherical. I mean, it's not, so as I said, there's a row parameter, spherical coordinates give all 3 dimensions, but if we fix the row parameter p1, this is our sphere. This is a very well-known coordinate system. And it's so this is, let me give you clearly, give you the domain here. This is mapping the domain, which I'll write this way, 0 to pi plus 0 pi. So in other words, the theta value is allowed to be between 0 and 2 pi. The phi value is allowed to be 0 pi, and it's mapping it to R3. In particular, it's mapping it to the sphere. Parameterizes. Given by this other equation, x squared c squared. So the question is, find tangent space of this unit sphere x, all points satisfying equation. Sorry guys, plus g, sorry. Okay. Find the tangent space to x. The computation. So there's 2 ways of doing it. You choose. And you give you p. So there's 2 ways. One is to use the parametrization. The other is to use the constraint. The parameter, and let's do both. All right, each group can do one. I know. So who's in what group? Guess what's in one? These are all prime. The right, to the right.
You have not.
You have, I know.
Person, we're not.
Okay, you're the group of 3. You have to be the group of 4. So do you want a parametric group and an implicit group? Okay, guys, be parametric. Yeah, 1 second. Sorry.
This is just. That's.
Yeah, we're now in, okay, so this is a subspace of R3. We're in R3, we're out of the torus was a warm up that I was preparing for you. This is a sphere in our. You're implicit.
Easy. Something. Fine.
Oh shit, guys. Parameter guys, this should be.
Oh, that makes much more sense.
Sorry, I'm sorry. This is on there.
Shouldn't affect the implicit people.
Yeah, sorry. I heard.
I was looking. That's. Then. So. That'd be. You actually choose five. To find DG and then insert and. Here.
Your notes on this one. I'll have to do a computation later to do this.
Oh, yeah. Alright. It's so deep, so. Like all the. This. Yeah. Each column that you. So like, you're like, doing like the same from that all the way. So that's you go down. D. Oh, wait. Math can't give one another one. Oh, we just create and sign like the good. Then you sign.
I mean, you can write it. Yeah.
They should be finished.
What's on? You have the, what's your, stick that.
Right. Exactly. You guys were supposed to finish first, so I messed you up. There. It's a little messier, but it's. Yeah, it maps it, boundaries. That's up. It's up.
What you do?
Okay.
Okay, so the other two. Yeah. But there's. Here. That's something. How does I use it? Inbound. There's. I agree with almost everything. So I looked at, so I'm looking at what point percent. Parameterization is the point of interest. Okay, so if I look at this parameterization. I want to go to this point, P. So what angle theta and phi give me this point? The easy thing to find first is that cosine of phi should be true. So for that, we know that phi should be pi over 2. So once you have phi is pi over 2, sine of phi is 1. And then you find out what theta is. Is that right? So I think we're a little over time, so let me just say this. The answer you got did involve solving, if it was a simple equation, solving a simple matrix equation. And what you did is you actually sort of made it a bit of a choice on the basis for the solution set. When you made that choice, that's fine. That gives you a parametrization of that point. What you'll get from this, from the parametric version, it's perhaps another parametrization of that same plan. And so it's very close, but it's not going to necessarily just be a multiple. We had an example. But it's the same image. All right, guys. Let's pick up on Monday. If people struggle with any of the homework, let me know and I can maybe go over a little bit of it. Yeah. Yeah, that's not right. I think there would be a second here. Okay, let me look and see. Maybe I updated it with a new second. Thank you. 23?
The last one is this.
Yeah, I meant 23.
The last second.
Sorry, yeah, 32 is, it's gonna come, a few weeks. Thank you. Yeah.
I'm really happy everything is very well.
Good, yeah, I can see that, right? I'm sorry for messing up the angle there, but yeah, no, this is very good because I see that, I think we want to do a lot more of this. A lot of this is, a lot of the computation, we work through a couple of them, like, oh, this, I understand how this works. And getting that method down will help and we'll get back to that abstract stuff. Good. You too.